going to be a long day. So we, as I said before, today we start to do some exercises. But first, in the first part of this morning, we keep on doing some more theory, and then in the second part of the morning, we start with some exercises. Okay, let us restart from where we left yesterday evening. We were talking about the probability density function, or the probability distribution of the gradient of the refractivity. And I put some number here. And let me remind you that this value is this so-called standard or median atmosphere. Median, you know what it means. It means that 50% of the time you will be below this value, and 50% of the time you will be above that value. So the median value is exactly the middle point of the distribution. Now all these ranges here between minus 157 and 0 is called normal or standard refraction. That is, every value within this interval is considered to be normal. Value bigger than 0 are called sub-refraction. And why it is sub will be clear in a moment. And values smaller than minus 157 are called super refraction. Now, let me just put some values here, and then we show you a diagram. Now, if you calculate the values of the radius of curvature of the electromagnetic ray and the equivalent radius for those three particular values, you find, we already know this, 27,000 kilometers. So those values are kilometers. And 8,500 kilometers for the equivalent radius. We have already seen this. When you have no refraction, that is, you have a zero gradient, the equivalent, the radius of curvature will be infinite. That is, If this is the real geometry, this is the Earth. For a zero gradient, the electromagnetic ray would propagate along a straight line. Radius of curvature equal to infinite means a straight line. And obviously, the distorted geometry will be identical to the real geometry. It's like having no atmosphere. What happens for larger values when you are in subrefraction? Something interesting happens, because the radius of curvature becomes all of a sudden negative. What does it mean to have a negative radius of curvature? What happens to the electromagnetic ray in this subrefraction area? Well, the electromagnetic ray will be actually bent towards the sky. And the radius of curvature of the Earth will be smaller. That is, the Earth, if you straighten this electromagnetic ray, the Earth will have a smaller radius, will be more curved. I will show the distorted geometry in a bit for the other situation. Now, what happens here? Something very interesting happens, because the raw value here is exactly the radius of the Earth. And what happens to your electromagnetic ray when its radius of curvature is exactly equal to the radius of the Earth? It travels perfectly parallel to the Earth's surface. And if the conditions are right, for example, like on the sea or water or very large flat area, this condition can last for several hundred kilometers. You will not be able to do all the travel around the Earth, because this situation is very unusual, but can last for quite a long time, over a few hundreds of kilometers. It's not unusual. So what will be the distorted geometry for this situation? What will be the equivalent Earth radius? You do the calculation, you find the equivalent Earth radius infinite. That is, the distorted geometry is a flat planet. So if you look at our distribution, what we consider to be normal situation is everything between those situations. Anything from 0 to traveling parallel to the Earth. Let's consider normal refraction situation. And eventually what happens for when you enter the super refraction region, where you have a radius of curvature in this region that is less than the radius of the Earth. So your electromagnetic ray would do something like this. This is a super refraction situation. And the equivalent Earth radius will be negative. A negative Earth radius would mean that your planet Earth will actually look like this, and the electromagnetic ray is always straight. So in a super refraction situation, you can really see, or you can really reach points that are well beyond your geometrical horizon. We're talking several hundred kilometers. It is not infrequent, for example, with avionic radars, airport radars, that they start getting echoes from mountains or from flat land that are very far from the Earth because of this phenomenon. Okay, now if we sum up everything into a slide, show you what I'll show briefly what we have said so far. Okay, in this slide that I sent you, you find real geometry with what is happening to the electromagnetic ray in super refraction situation. This is what happens to the K factor, that is 0 to minus infinity, so it's negative here. So you got also a negative equivalent Earth radius. Remember that the equivalent Earth radius is the Earth radius multiplied by the scale. And you are in super refraction. This is Italian, but the thing is better in English. Super refraction, super refraction situation. And this is going to be the Visconti zone. Then we are in super refraction limit, normal refraction, up to super refraction situation. Again, in this case, the electromagnetic ray is bent towards up, and the Earth is towards down. Okay, so how do you design a radio system in a situation like this? You understand that you can only do a statistical design of the system. That is, you have to take into account, and now we go back to our distribution, you have to take into account the statistical distribution of the refractive index gradient and design the system so that it will work for a given percentage of time. Now, before we tackle this problem, let's see how do we design a system if we know the equivalent earth radius. And then we link this information to the statistical information of the atmosphere. So what if we are going to okay, to explain how you use the equivalent earth radius to design, calculate the coverage of your system, we assume a flat length, flat planet. We assume it's not flat. The Earth is not flat. We assume there are no obstacles. So the first question to answer is, we have our planet, and as we know, the radius that we have to consider is the equivalent Earth radius, because that's the radius that is significant from a radio communication point of view. The first question is, what is the coverage? The coverage, we mean what is the maximum distance that our radio signal can reach over transmitters located on a tower obviously you cannot locate an antenna transmitter on the ground because otherwise the coverage would be very small. But let's assume that we install our antenna on a tower that is h meters high. We ask, what is the coverage of this transmitter? Well, if we use the equivalent earth radius, the coverage will be clearly given by the tangent point so any point from the tower to this point here that I indicate as XA, from 0, any point whose distance on the ground is from 0 to XA is visible from the tower. So will be covered. We are assuming now isotropic radiator. So we are not taking into account for the moment the directivity function of the antenna. So any point here is covered by our transmitter. The points that are further away will be below the horizon. So those points here, in theory, will not be covered. It's not completely true because there is another mechanism. It is called diffraction. It will tackle later on. But in principle, that's the maximum coverage. So how do we determine this distance? Again, the best option is to model the spherical surface with a parabolic approximation. Parabolic approximation means simply that h is equal as simple as that. And you can solve this equation if you want. If you have the height of the tower, you can solve this equation for XA. Or if you want to cover a given area, you know XA, you know the maximum distance that you want to reach, and you calculate the height of the tower. What's the problem here? The problem is that the equivalent radius is continuously changing. So this point is moving closer or farther away with time. Which value do we choose for equivalent earth radius? And then how tall must be our tower? We have to do this design statistically. And we will discuss briefly now, but then we do exercises to understand this concept. Questions so far? Before we put a little another. Now this is a kind of point to multi-point coverage, kind of broadcast transmitter. What changes if you want to make a point-to-point connection? That is, for example, you want to design a microwave link and the transmitters and receivers are both on towers. Well, the geometry changes only a little bit because if this is the Earth, now you have two towers. They do not need to be equal. We are connecting point A to point B. And this is the limit situation. So if you call this segment XA and you call this one XB from here, the total distance for this geometry, the total distance x will be XA plus XB. The total length of the link. And for each one of those quantities, you can use parabolic approximation. The question, yes, please.
Can we use the average for in the first question for the radius?
The average. If you use the average value, your system will be working for 50% of the time. Because for 50% of the time, you will be, this point will be visible, and for 50% of the time, this will be below the horizon. So the median, usually the median or standard atmosphere value is not a satisfactory value because the system will not be working for 50% of the time. You have to take more margin. This means your towers must be higher. But that was a very good question. Okay, so if we use the parabolic approximation for both of them, we can write this as and you can also solve this equation for whatever value you want. If you want to know the distance, the maximum distance that you can cover if you know the height, or you can choose the height if you want to cover anything. And please note that the towers do not need to have the same height. You can, depending on your personal choice or your constraints, you can have different values for the two towers. Now the problem is how to link those equations to our statistics. We will do more practice during the exercise, but just let me anticipate how do we proceed. We have this distribution. Let me draw the distribution here. What we really need to know is not the probability density function, but the so-called cumulative distribution function. That is, if you take a given value of x, well, we are really interested in the probability that, so if you call this variable x bar, whatever, what you are really interested in, for example, is the probability that this value is not exceeded, or the probability, depending on your application, that this value is exceeded. One of the two, whichever fits your needs. Now, we most often use this probability. Now, what is the probability for this variable to be smaller than an arbitrary value? How do you calculate the probability of an event if you have the probability density function? You calculate the integral. The probability of this event is the integral from minus infinity to this value of, if this function, we call it fx, is the area that I shaded there. Now, I don't want to anticipate what we are going to find later on, But the idea is we have to define a satisfactory probability for our system. And then we find some condition that says, okay, your system works if the probability of this event is smaller than. So we decide which is the probability of this event, and then we calculate the value itself. We decide the probability, and from the probability we obtain this value. And we use this value to calculate the equivalent temperature. At this time it's a little bit confusing, I understand, but it will be clearer with exercise. Sometimes we can be interested. Oh, just let me. Now, if you make a plot of this function, please remember that the probability is always between 0 and 1. If this is this function, that is the probability for our gradient to be less or equal to the value on ordinate, you will find something like this. And the 0.5, that is 50% of the probability, will be our median atmosphere. In other words, this curve here is the integral of this one. And it goes from 0 to 1 because the integral of the probability density function is 1. Probability of any, the total probability of any event in this case is 1. Sometimes we may be interested into this other probability, and the probability for the gradient to be bigger than a given value is the complementary this probability is obviously the integral from x to plus infinity is the other part of the distribution. And if you want to make a graphic of this, cumulative distribution, this is called the cumulative distribution function, just for your information. This thing is going to be like this, the complementary. And again, the 0.5%, the 50% is minus 2%. So one is the non-exceedance probability, and this is the exceedance probability. And one is one minus the other. So the probability just for your convenience. So if you have one, you can go from one to another simply with this simple equation. Now, we will use those statistics later on in doing our system design. I will not add anything else at the moment on this topic. Questions? Before we move to the diffracted wave? Okay, diffraction.
Y 3 meses después, en novillas. Yo fundamento matemático. No nada que ver con
Now, the topic that we tackle now is propagation over irregular terrain. That is, we are going to see the diffractive wave. That is quite important for our application. Because it allows radio communication even if there is no direct path between the transmitter and the receiver. Even if there are obstacles between transmitter and receiver. What we're going to see, how we structure this lecture. First, we start with some basics of the diffraction theory. We don't go too much into the electromagnetic details. Something I will not demonstrate everything because otherwise it will be tedious. But there are some few things that you must know. So we start with the so-called Fresnel zone ellipsoids. This is important because you will discover that when you make a radio link between 2 points, it is not enough to leave the direct path clear from obstacle. You must leave an area around the line connecting transmitter and receiver free from obstacles if possible. This area is called the first Fresnel ellipsoid. And this is most important when you design typically point-to-point links. Then we talk about diffraction losses, so-called knife edge. It is, we will discover, or we will learn, that even if, let me anticipate those concepts. Okay, the first concept, the Fresnel ellipsoid that I said is that you want to connect point A to point B. You must leave a region around the link free from obstacles, if possible. Not just the direct geometrical link. Not just the direct path, but an area around the link. The second concept, diffraction losses, is like this. if you have a sharp obstacle and you have a transmitter here and a receiver here, and the obstacle is perfectly opaque, cannot be penetrated, you still have the possibility to make a radio connection, because the electromagnetic wave will actually be diffracted by this obstacle. But there will be extra losses with respect to free space. So you will learn how to calculate simply those losses, this extra attenuation, with respect to free space. But quite often the communication is still possible, even if transmitter and receiver do not see each other. Then we will learn how to tackle the problem of multiple edges, multiple obstacles, that is, same situation, but you have different obstacles. How do you calculate the extra losses in this case? For example, this is typical of buildings in a town, for example. You have several buildings, and you want to know what is the extra attenuation. In other words, you want to know if it is easier to pass over the buildings or around those buildings. You will see that quite often in urban environment, losses are lower if you go around the buildings, if the transmitter and receiver are at the ground level. And eventually we will put all these things together and we see the so-called path loss prediction methods. We start looking at a family of prediction methods that are called the empirical prediction. I will present you those methods. Those methods have already been implemented in software. Some software is also freely available over the net, over the internet. So if someone is interested in this, something you can play with. So that's the structure. Let's start with the first point. Fresnel zone ellipsoid. This is slightly more complicated than the rest. But we need to know something about it. Okay, everything starts with the so-called Huygens principle. This is quite an obscure electromagnetic principle. It states something like that. Imagine that you have a plane electromagnetic wave. I am drawing the range. So this plane electromagnetic wave is propagating in that direction. This thing here is the so-called wavefront. We called that yesterday also constant phase equiphase, equiphasing surface of the wave. Now, the Huygens principle, as I said, is quite difficult to accept, but it can be demonstrated, but we won't do that. Says that something like that. Each point of the wavefront the wavefront is something that is not material. The wavefront is just an imaginary surface. There is nothing there that can be vacuum. But each point of the wavefront acts as a source. In other words, like a small antenna of a secondary wavelength. I will make a drawing later. And those waves combine to produce a new wavefront. In the direction of propagation. You will find there's more details on this on the book that I gave you. So far I'm following the book. So let me explain this principle in human words. What the Huygens principle is stating is that we know that the wave propagates from this wavefront after some time. It propagates to a new wavefront. And the Huygens principle says it is equivalent, this propagation mechanism is the same that you would have. If on those wavefront you have many small antennas that are radiating small waves. Those infinite small antennas on this wavefront generate the new wavefront. There is nothing there, huh? Those antennas do not exist. But it's exactly as if there were some antennas. This is important because when you have an obstacle, the effect of an obstacle, and we shall this in a moment, the effect of an obstacle here, if you have a wall or anything, is to block that part of the wavefront, that part of the virtual antennas. But those parts are still radiating. So there will be, and we will see, we will quantify this, there will be some energy radiated from those virtual antennas reaching beyond the obstacle. But this is also a common experience that if you have a window, you don't go from light to dark. The light is entering the window, but on the side of the window you have shadow. That shadow, so this is the so-called shadow area. the shadow here is given by the radiation of those Huygens sources. I'm not demonstrating this. You have to take this for granted. But you can use this mechanism to calculate the electromagnetic field that you have in shadow regions, where the receiver does not directly receive the electromagnetic field. And that's what we're going to do. We're going to use this principle to calculate the electric field beyond the obstacle. Before I do that, questions? How do we do? First of all, we have to calculate what is the power or the intensity of those imaginary or virtual antennas that are radiating. Now, if you take a small area here, let's imagine that you take a very small area of this plane. So let me zoom. It's a very small area. We call this, the area is the total area is this. This is infinitesimal, so it's one value. And on this area you have all your sources. Now you ask, the question is, let's assume that the incident wave, the plane wave that is propagating, has an electric field whose magnitude is E0.